John Dalton, born in 1766 and passing away in 1844, is a seminal figure in scientific thought. Born in a modest Quaker family in Cumberland, England, his contributions to the field of science, particularly chemistry, have been instrumental in shaping our understanding of the natural world. His most transformative work focused on the modern atomic theory, a groundbreaking framework that fundamentally altered how scientists perceive matter and its myriad interactions. Despite facing financial constraints, Dalton's early life was marked by a hunger for academic pursuits. Encouraged by his Quaker upbringing, which valued education, Dalton was largely self-taught and began teaching at a local school when he was only 12. He eventually moved to Manchester, where he joined the Manchester Literary and Philosophical Society. This association allowed him to interact with other intellectuals and publish his research. By this time, Dalton had already published essays on meteorology and color blindness, a condition he experienced. These works were early indicators of his analytical mind, which he later applied to decipher the complexities of chemical substances. When examining Dalton's profound impact, it is crucial to delve into the intellectual environment of his era. Before Dalton, the concept of the atom was not entirely new. However, theories propounded by early thinkers like Democritus were more philosophical and lacked empirical validation. During Dalton's lifetime, chemistry was still a fledgling field, often considered a subset of alchemy. Scientists of the day lacked a unified theory to understand why and how elements combine in specific ratios to form compounds. The prevalent model, the phlogiston theory, often offered inconsistent or inaccurate explanations. It was in this milieu that Dalton introduced his atomic theory in the early 19th century, initially outlined in 1803 and later elaborated in his book A New System of Chemical Philosophy in 1808. Dalton proposed that matter is composed of indivisible particles called atoms. Contrary to previous theories, Dalton provided quantitative methods to prove his assertions. His theory was revolutionary in several aspects. Firstly, he asserted that all atoms of a given element are identical in mass and properties. Secondly, compounds are formed when atoms of different elements combine in fixed, simple ratios. Lastly, atoms are neither created nor destroyed in chemical reactions, instead, they merely rearrange to form new compounds. Dalton utilized chemical formulas to represent compounds, showing atoms as symbols and their proportions as numbers. This advancement paved the way for future scientists to explore chemical reactions with more precision. He also introduced the concept of atomic weights, offering a method to compare the masses of different atoms. Such advances led to the formulation of the periodic table and were crucial in enabling subsequent discoveries in chemistry. The reception of Dalton's atomic theory was one of cautious optimism. While the scientific community found the quantitative nature of his methods compelling, some skeptics pointed to limitations, especially concerning the measurement of atomic weights. However, as methods improved and other scientists, such as Amadeo Avogadro and Dmitry Mendeleev, built upon Dalton's foundation, the theory gained widespread acceptance. It is the cornerstone of modern chemistry, physics, and even biology, extending its influence to diverse scientific domains. Dalton's work had a transformative effect not only on science but also on industrial applications. His ideas were found to be practical in metallurgy, pharmacology, and chemical engineering. By understanding atomic structures, researchers could develop new materials and medicines with increased efficacy. Furthermore, Dalton's principles laid the groundwork for later quantum mechanics and nanotechnology developments. While Dalton's atomic theory underwent several refinements and faced challenges, its essence has remained intact. In fact, the advent of technologies like X-ray crystallography and electron microscopy has reinforced Dalton's original postulates. His approach to scientific inquiry, combining rigorous experimentation with theoretical constructs, is an enduring example of how science should be conducted. Moreover, Dalton's legacy extends beyond his academic contributions. A committed Quaker and social reformer, he espoused the virtues of intellectual rigor and moral integrity. His scientific curiosity was matched only by his commitment to improving society, a rare blend that makes him an enduring role model for scientists and citizens alike. As we reflect on the life and work of John Dalton, we can discern the indelible mark he left on science and human understanding. Dalton's modern atomic theory not only redefined the fabric of chemistry but also bridged gaps between disparate fields of science. In so doing, Dalton emerged not merely as a chemist of repute but as a transformative intellectual whose ideas continued to influence scientific thought and real-world applications. His legacy is a testament to the power of curiosity, rigor, and the enduring quest for knowledge. Dalton's contributions to chemistry and atomic mass. John Dalton, a remarkable figure in the annals of science, was born on the 6th of September 1766 in Eaglesfield, Cumbria, England. Though his name often evokes associations with meteorology due to his groundbreaking work on the behavior of gases in the atmosphere, his legacy extends far beyond this realm. His profound contributions to chemistry, the development of the atomic theory, and the concept of atomic mass have indelibly shaped our understanding of the natural world. Dalton hailed from a Quaker family with modest means. Despite the limitations of his early education, his relentless pursuit of knowledge led him to contribute original insights that have become the cornerstone of modern chemistry. His thirst for understanding was partly fueled by his engagement with Manchester's burgeoning scientific community, where he was an active Manchester Literary and Philosophical Society member. As early as 1803, Dalton proposed that elements could be distinguished by the weights of their atoms, a genuinely revolutionary concept at the time. This fundamental idea sprang from his work with gases, in which he had been attempting to explain why elements always react in ratios of whole numbers. For instance, water always consists of hydrogen and oxygen in the ratio of 2:1 by volume, which Dalton explained through the relative weights of hydrogen and oxygen atoms. To understand the monumental impact of Dalton's theory, one must appreciate the scientific context in which it was presented. At the turn of the 19th century, chemistry was still developing, straddling the line between alchemy and systematized field of study. Dalton's atomic theory offered a robust framework to explain chemical reactions, one that was rooted in empirical data and mathematical rigor. Dalton provided a crucial key for accurately understanding and predicting chemical reactions by postulating that atoms combine in fixed ratios to form compounds. Moreover, Dalton's theory laid the groundwork for the concept of atomic mass, a standard measure still utilized in contemporary science. For Dalton, atomic mass served as a convenient tool for comparing the weights of various atoms, thereby enabling the classification of elements based on these weights. Though his measurements were not entirely accurate due to the limited technology of his time, the principle itself has stood the test of time. His ideas were instrumental in developing the periodic table and facilitated advancements in various fields such as physics, geology, and even biology. Dalton's contributions did not go unnoticed during his lifetime. His work quickly gained acceptance among his contemporaries, partially due to the convergence of various empirical data that corroborated his theories. Nonetheless, the road to scientific recognition was not entirely smooth. Dalton faced staunch opposition from some quarters, most notably from those who were skeptical of any theory that delved into the unseeable world of atoms. However, Dalton's rigorous empirical methodology and the predictive power of his theory ultimately won the day. Scientists such as Amadeo Avogadro and Dmitri Mendeleev built upon Dalton's pioneering work in the following years. Avogadro refined the definition of a molecule and introduced Avogadro's law, which provides insights into the behavior of gases at a molecular level. On the other hand, Mendeleev constructed the periodic table based on atomic masses, a clear testament to the lasting influence of Dalton's contributions. Similarly, the 20th century discovery of isotopes, atoms of the same element with different masses, only served to refine and not refute Dalton's original theories. Beyond the scientific community, Dalton's work also had significant implications for industry. His principles found application in chemical engineering, thus playing a role in developing synthetic materials, pharmaceuticals, and a host of other manufactured goods. Indeed, The Industrial Revolution was greatly facilitated by an enhanced understanding of chemical processes, an understanding significantly bolstered by Dalton's work. One of the intriguing aspects of Dalton's life is that he achieved all this while grappling with color blindness, a condition later known as Daltonism in his honor. Though this condition posed a personal challenge, it did not deter him from delving into complex areas of study that required an astute sense of observation and keen analytical skills. While Dalton passed away on the 27th of July 1844, his ideas continued to live on, invigorating multiple fields of scientific inquiry. We owe much of our understanding of chemistry and atomic structure to this luminary. John Dalton, a man of humble beginnings but extraordinary intellect, substantially altered our perception of the world at its most fundamental level. In recognizing the weight of Dalton's contributions, we gain a deeper appreciation for the transformative power of scientific thought. Dalton's legacy, cemented in the laws and theories that bear his name, confirms his place as a titan in the scientific pantheon. The impact of Dalton's atomic theory on scientific understanding. John Dalton, a prominent English chemist and physicist born in 1766, revolutionized the field of science with his seminal work on atomic theory. His theories laid modern chemistry and greatly influenced other scientific disciplines, including physics and biology. The impact of Dalton's atomic theory on scientific understanding is far-reaching, offering new insights into the nature of matter and setting the stage for subsequent discoveries. John Dalton was initially inspired by the experimental work of Antoine Lavoisier and Joseph Louis Proust. Lavoisier had laid the groundwork for the law of conservation of mass, while Proust had proposed the law of definite proportions. Intrigued by these laws, Dalton considered how they might fit into a more extensive framework. Thus, his atomic theory was born, challenging long-standing notions and propelling science into a new age of empirical rigor and conceptual clarity. Dalton's atomic theory was groundbreaking and fundamentally altered the scientific perception of matter. The theory posited that all matter consists of indivisible atoms, each with its distinct weight. Moreover, Dalton proposed that these atoms could combine in fixed ratios to form compounds, providing an elegant explanation for the law of definite proportions. His theory provided a conceptual framework for understanding chemical reactions and paved the way for various scientific innovations and discoveries. One of the most immediate impacts of Dalton's theory was its application to the burgeoning field of chemistry. Before Dalton, the idea that elements were composed of discrete, individual particles was only a notion. However, Dalton's theory offered a concrete conceptual framework that could explain chemical reactions. By advocating that elements combined in specific ratios by mass, Dalton offered chemists a tool for identifying unknown substances and creating new compounds. His theory thus ushered in a new era of scientific investigation, facilitating the discovery of new elements and compounds and bringing unparalleled rigor to experimental design. Additionally, Dalton's atomic theory profoundly influenced physics, particularly in the development of thermodynamics. The notion that matter was composed of discrete atoms made understanding phenomena like pressure, temperature, and volume more manageable. James Clerk Maxwell and Ludwig Boltzmann later extended Dalton's ideas, using them as a basis for the kinetic theory of gases, which further elaborated the behavior of particles at the molecular level. Besides its application in physics and chemistry, Dalton's atomic theory also played a crucial role in advancing biology. The idea that atoms combine in fixed ratios to form compounds facilitated a deeper understanding of biological molecules, such as proteins and nucleic acids. By highlighting the foundational role of atoms in the structure of matter, Dalton's theory provided a conceptual stepping stone for scientists like Francis Crick and James Watson to decode the structure of DNA. Consequently, this understanding proved instrumental in the development of molecular biology, shaping contemporary perspectives on genetics, disease, and cellular function. Furthermore, Dalton's atomic theory contributed to the evolution of scientific methodology. His theory encouraged empirical testing and rigorous observation, setting a new standard for scientific investigation. It opened doors for more accurate data collection and interpretation, revolutionizing how experiments were designed and conducted. The scientific community embraced Dalton's insistence on empirical validation, which facilitated the pursuit of more advanced and nuanced research projects. The work of Dalton had an international impact, transcending cultural and linguistic barriers. His theories became the subject of study and discussion among scholars around the globe, offering a universally applicable framework for the scientific investigation of matter. Dalton's atomic theory has been refined and extended over the years, but its core principles remain as relevant today as they were in the early 19th century. Modern scientific developments like quantum mechanics and nanotechnology owe much to Dalton's pioneering efforts. In reflecting upon the legacy of John Dalton, it becomes evident that his atomic theory has been a cornerstone in the edifice of modern science. From revolutionizing the discipline of chemistry to influencing the fields of physics and biology, Dalton's contributions have had an enduring impact. Moreover, his emphasis on empirical methods has fundamentally changed the landscape of scientific research, fostering an environment of rigorous investigation and continuous discovery. Dalton's atomic theory has not only deepened our understanding of the natural world but also equipped us with the tools to further explore the intricacies of matter. His work serves as a testament to the transformative power of scientific thought, encouraging us to continually question, investigate, and innovate. Dalton's work in meteorology and color blindness. John Dalton, a prominent English chemist and physicist, made groundbreaking contributions to various scientific fields in the late 18th and early 19th centuries. While Dalton is predominantly celebrated for his pioneering work in atomic theory, his lesser-known but equally significant contributions to meteorology and the study of color blindness deserve attention. Born in 1766 in Cumberland, England, Dalton's love for science was evident from a young age. In 1793, he moved to Manchester and joined the Manchester Literary and Philosophical Society, where he gained exposure to scientific discussions and found an audience eager to listen to his insights. His work in meteorology began to take shape here, motivated by a keen interest in understanding the natural world. Dalton meticulously recorded meteorological observations from a very young age, making daily entries about the weather for 57 years without fail. He presented his first paper on the subject to the Manchester Literary and Philosophical Society as early as 1793. Dalton proposed that air is a mechanical mixture of gases rather than a chemical compound. This led him to investigate the role of water vapor in the atmosphere, making him one of the earliest scientists to discuss the concept of humidity. Dalton was the first to elucidate that the quantity of water vapor the air can hold increases exponentially with temperature. His experiments on dew point and evaporation also yielded essential empirical formulas. Furthermore, Dalton initiated the practice of displaying weather data graphically, which enabled better predictive models. He standardized meteorological observations by introducing consistent measurements and charts, allowing for more accurate and meaningful comparisons. Dalton's systematic approach laid the groundwork for modern meteorology, and his dedication set a new standard for empirical scientific investigation. In tandem with his meteorological pursuits, Dalton also made pioneering strides in the understanding of color blindness, a condition that he experienced. Intriguingly, his inability to distinguish specific colors did not deter him, it catalyzed his curiosity. Dalton was the first scientist to examine this phenomenon rigorously and explain it scientifically. His initial paper on the topic, presented in 1794, was perhaps the first recognition of the condition in a scientific forum. He hypothesized that the condition resulted from a discoloration of the aqueous humor, the liquid medium in the eyeball. While this theory was later proven to be incorrect, Dalton's work was seminal in drawing attention to the hereditary nature of the condition. His contribution led to the condition frequently termed Daltonism in his honor. Dalton meticulously examined the perceived colors of various substances under daylight, candlelight, and through multiple media. His detailed observations, while founded on erroneous initial assumptions, paved the way for later research that eventually led to identifying photoreceptor cells in the eyes as the actual cause of the condition. Although Dalton's theories in meteorology and color blindness were not entirely accurate in the light of modern science, his approach to the investigation was pioneering. He applied systematic methods and empirical reasoning that set the stage for later scientists. Moreover, Dalton's work in these fields often informed and influenced his more renowned atomic theories. For instance, his meteorological observations of atmospheric pressure and his empirical formulas on gases contributed to his atomic theory's formulation. Dalton's achievements in meteorology and color blindness exemplify his versatility and depth as a scientist. His relentless pursuit of understanding the complexities of the natural world left an indelible imprint on scientific history. His meticulous observations and innovative techniques have been adopted and refined over time, confirming their value and significance in the scientific community. As we reflect on Dalton's broad scientific legacy, it is evident that his work extended far beyond the realm of atomic theory, for which he is most renowned. His rigorous methods in meteorology set the foundations for modern-day weather science, and his early studies on color blindness opened a new avenue of research in ophthalmology. Indeed, Dalton's insatiable curiosity and exacting methods make him not just a chemist or physicist but a polymath whose scientific contributions are both profound and enduring. Dalton's influence on the development of the periodic table. John Dalton, an eminent British chemist and physicist born in 1766, indelibly shaped the course of scientific inquiry into the nature of matter. Although Dalton did not directly develop the periodic table, his pioneering work on atomic theory laid the essential groundwork upon which later scientists built. Today, Dalton's influence pervades modern chemistry, offering a fundamental framework that has enabled successive generations of researchers to categorize and understand the behavior of elements. Indeed, Dalton's theories serve as the cornerstone for constructing the periodic table, an iconic tool used ubiquitously in chemistry today. Born into a Quaker family in Cumbria, England, Dalton was primarily self-taught. Despite his limited formal education, he demonstrated an unquenchable thirst for knowledge early on. This insatiable curiosity led him to his groundbreaking work on gases, including developing Dalton's law of partial pressures. Not content with merely contributing to understanding gaseous behavior, Dalton focused on the nature of matter itself. He formulated his atomic theory through rigorous experimentation and observation, positing that matter consists of indivisible atoms, each unique to a specific element. Dalton's atomic theory broke new ground by proposing that atoms could neither be created nor destroyed, only rearranged. This theory was instrumental in explaining why elements always combine in fixed ratios and thus proved revolutionary in understanding chemical reactions. Furthermore, Dalton's theory offered explanations for the principles of conservation of mass in reactions and the concept of multiple proportions. By delineating the atomic structure of elements, Dalton provided future scientists with the necessary tools to begin thinking about the organization of these elements logically and systematically. Among those profoundly influenced by Dalton's ideas was Dmitry Mendeleev, the Russian chemist responsible for devising the periodic table in its early form. As Dalton had previously described, Mendeleev's periodic table arranged elements by atomic mass, a property directly linked to the number and arrangement of atoms. The brilliance of Mendeleev's table was its ability to leave gaps for yet-to-be-discovered elements, effectively predicting their existence and properties. Over time, with the modification of arranging elements by atomic number rather than atomic mass, the modern periodic table emerged, serving as a testament to Dalton's early theories on atomic structure. In addition to laying the foundation for the periodic table, Dalton's theories profoundly impacted the chemistry discipline. Before Dalton, chemistry was often seen as an amalgam of alchemy and empirical observations, lacking a unified theoretical foundation. Dalton's work injected a much-needed sense of scientific rigor and methodology into the field. As a result, chemistry transitioned from a collection of isolated facts into a coherent discipline rooted in the principle of atomic theory. Moreover, Dalton's influence transcended the boundaries of chemistry. His atomic theory was crucial in shaping the kinetic theory of gases, providing insights into the thermal properties of matter. These principles laid the groundwork for thermodynamics, a field integral to physics and engineering. Thus, the repercussions of Dalton's work are felt not only in the corridors of chemical laboratories but also in the broader spectrum of scientific endeavor. Nevertheless, it is worth acknowledging that Dalton's theories had limitations. His model of the atom as a solid, indivisible sphere was later supplanted by more intricate models that considered subatomic particles. Despite this, the core tenets of his atomic theory have withstood the test of time and remain fundamental to our understanding of the material world. As the periodic table continues to evolve, with new elements discovered and our understanding of atomic behavior becoming increasingly nuanced, the foundational role played by Dalton cannot be overstated. His atomic theory served as the stepping stone for the logical arrangement and understanding of elements, culminating in the creation of one of the most vital scientific tools today, the periodic table. Dalton's contributions to the scientific community were, without a doubt, monumental. They exemplify how the work of one diligent and inquisitive mind can set the stage for centuries of discovery. By providing a systematic approach to the study of matter, Dalton helped to transform not just the field of chemistry but the scientific enterprise. While it's true that Dalton did not live to see the development of the periodic table, his pioneering theories made its construction inevitable. Indeed, every scientist who utilizes this indispensable tool is, knowingly or not, paying homage to Dalton's revolutionary insights into the very fabric of matter.